Morning everyone, I am Moni from Basic Chemistry first year. Today I am reading chapter Thermodynamics. It is a part 2 and it is a visual impaired reading. Standard enthalpy of formation. The standard enthalpy changes for the formation of one mole of compound from its elements in their most stable state of the aggregation, also known as the reference. It's called the standard molar enthalpy of formation. It is a symbol of this, where the subscript F indicates that one mole of the compound in a question has been formed in its standard states from its element in their most stable state of aggregation. The reference states of the element in the most stable state of aggregation at 25 degrees Celsius and 1 bar pressure. For example, the reference state of dihydrogen gas and those of dioxygen, carbon and sulfur are O2 and carbon graphite and sulfur respectively. Some reactions with the standard molar enthalpy of formations are as follows. The following, it is important to understand that the standard molar enthalpy of formation is just a special case of enthalpy of formation where one mole of the compound is formed from one constituent element as the above three equations where one mole of each water, methane and ethanol is formed. It contrasts the enthalpy changes from exothermic reaction. It is not an enthalpy of the formation of calcium carbonate, since the calcium carbonate has been formed from other compound and not from its constituent elements. Also, for the reaction given below, enthalpy changes is not a standard enthalpy of formation. Here the two moles instead. Here the two moles instead of one mole of the products, it is formed from the elements. Therefore, by dividing all coefficient in the balanced equation by 2, expressing for the enthalpy of formation of HBr, it is written by this. Standard enthalpy of formation of some common substrates are given in table 5.2. Y conversion standard enthalpy for formation of an element is a reference states. It is the most stable state of aggregation. It taken to be 0. Suppose you are a chemical engineer and want to know how much heat is required to decompose calcium carbonate to lime at a carbon dioxide with the substance in their standard states. Thermochemical equation, it is a balanced chemical equations together with the values of its delta charge. It is called a thermochemical equation. We specify the physical state of the substance. It is the equation. For example, the above equation describes the combustion of the liquid ethanol at constant temperature and pressure. The negative sign of enthalpy changes indicates that it is an exothermic reaction. It would be necessary to remember the following conversion regarding the thermochemical equation. The coefficient it is balanced thermochemical equation refers to the number of moles or a reactant and product involved in the reaction. The numerical values refers to the numbers of the moles of a substance specified by the equation. Standard enthalpy changes will be have a unit as a kg per mole. To illustrate the concept, let us consider the calculation of heat of reaction for the following reaction. For the table 5.2, the standard enthalpies of the formations are following. Note the coefficient used in these calculations for a pure number which are equal to the positive stereometric coefficient. The unit for this is a kilojoule per mole, which means per moles of the reactant. Once we balance the chemical equation in the particularly way as above, that define the moles of the reaction we will had if we have the balance the equation definitely. For example, everyone. I'm Moni from Basic Chemistry. Thermochemical equation. A balanced chemical equation together is the values of its is called the thermochemical equation. We specify the physical states of a substance in the equation in the following. It would be necessary to remember the following convention regarding thermochemical equation. The coefficient in a balanced thermochemical equation refers to the number of moles of a reactant and product involved in the reaction. The numerical values refers to the numbers of the moles of a substance specified by the equation. Standard enthalpy changes will have a unit as kilojoule per mole. Hess law of a constant heat combustion. We know that the enthalpy is a state function, therefore which changes the enthalpy is independent of the path between initial state and the final state. In other words, the enthalpy changes for that reaction is the same without whether it occurs in one step or it's a series of steps. This may be started as follows in the form of Hess law. It If a reaction takes place in a several steps, then its standard reaction enthalpy is the sum of the standard enthalpy of the intermediate reactions into which the overall reaction may be divided at these same temperatures. Let us understand the importance of this law with the help of the example. Consider the enthalpy changes for the reaction. Carbon in graphite form plus oxygen gives the carbon monoxide. Although carbon monoxide is a major product, some CO2 gases is always produced in the reaction. Therefore, we cannot measure the enthalpy changes for above reaction directly. However, it can find some other reactions involving related species. It is possible to calculate the enthalpy change for above reaction. Let us consider the following reaction. Carbon plus oxygen gives carbon dioxide. We can combine the above two reactions in such a way so as to obtain the desired reaction to get 1 mole of carbon monoxide on the right. We reverse equation in this heat is absorbed instead of being released, so we changes the sign. Enthalpies of a different types of the reaction. Standard enthalpy of combustion. Combustion reactions are exothermic in nature. These are the important in industries, rocketry and other walls of the life. Standard enthalpy of combustion is defined as the enthalpy changes per mole of a substance when undergo combustion and all reactants and products being in their standard states of a specified temperature. Cooking gases in a cylinder contain mostly butane. During complete combustion of 1 mole of the butane, 2658 kilojoule of heat is released. We can write the thermochemical equations of these are following. Similar combustions of the glucose given out 2808 kJ per mole of heat. Our body also generates the energy from 4 by same overall processes as combustion. Although final products are produced after a series of complex biochemical reactions involving agents. Bond enthalpy. The chemical reactions involves the breaking and making of a chemical bond. Enthalpy is required to break a bond and energy is released when a bond is formed. It is possible to relate the heat of reaction to change in energy associated with breaking and making of chemical bonds. With reference to the enthalpy changes associated with the chemical bonds, two different terms are used: thermodynamics, bond as dissociation enthalpy, and mean bond enthalpy. Let us discuss these terms with reference to diatomic and polyatomic molecules. Diatomic molecules consider the following process in which the bonds in one of dihydrogen gas is broken. The enthalpy change involved in the process is the bond dissociation enthalpy. The bond dissociation enthalpy is the changes in enthalpy when one mole of a covalent bond of a gaseous covalent compound is broken to form products in a gaseous phase. Note that it is the same as the enthalpy of the atomizations of dihydrogen. This is a true for all diatomic molecules, for example, chlorine, oxygen. In the case of polyatomic molecules, bond dissociation enthalpy is different for different bonds within the same molecule. Polyatomic molecules, let us now consider a polyatomic molecule like methane. The overall thermochemical equation for its atomization reaction is given below. In methane, all the carbon-hydrogen bonds are identical in bond length and the energy. However, the energies required to break the individual carbon-hydrogen bond in each successive steps differ. We find the mean carbon-hydrogen bond enthalpy in a methane. It has been found the mean carbon-hydrogen bond enthalpy differs silently from compound to other compound, but it does not differ in a greater deal. Using Hess law, bond enthalpy can be calculated on the enthalpy values of some singles and multiple bonds given in table 5.3. The reaction enthalpies are very important quantities as these rise from the changes that accompany the breaking of old bonds and the formation of the new bonds. This relationship is particularly more useful when the required values are not available. The net enthalpy changes of a reaction is the amount of energy required to break all the bonds in the reactant molecules means the amount of energy required to break all bonds in the product molecule. Remember that these relationships is approximate and valid when all substances are in the reactions are in gaseous state. Lattice enthalpy. The lattice enthalpy of an ionic compound is the enthalpy changes which occur when one mole of ionic compound dissociates into its ion in a gaseous state. Since it is impossible to determine the lattice enthalpy directly by experiment, we use an indirect method. We can construct an enthalpy diagram called the Born-Haber cycle. Let us now to calculate the lattice enthalpy by following steps given below. Any solid gives any gas, sublimation of the sodium any gas into any gas plus one electron lose the ionization energy of sodium atom. The dissociation of the chlorine at the reaction enthalpy is half of the bond dissociation enthalpy. Electron gained by a chlorine atom. The electron gained enthalpy is, you have learnt about ionization enthalpy, electron gain enthalpy in Unit 3. In fact, these terms have been taken from thermodynamics. Early terms ionization energy and electron affinity were in practice in place of above terms. Enthalpy of solution. Enthalpy of solution of a substance is the enthalpy changes when one mole of it is dissolved in a specified amount of solvent. The enthalpy of solution at infinite dilution in the enthalpy change observed on dissolving the substance in an infinite amount of solvent when the interaction between the ions are negligible. When an ionic compound dissolves in a solvent, the ions leave their ordered position on a crystal lattice. These are now more free in solution, but solvation of these ions also occurs at the same time. This is shown diagrammatically for the ionic compounds. Enthalpy of diffusion, it is known no it is known that enthalpy of a solution is the enthalpy changes associated with the addition of specified amounts of solute to produce the specified amount of solvent at a constant temperature and pressure. This argument can be applied to any solvent with a slight modification. Enthalpy changes for dissolving 1 mole of gaseous hydrogen chloride in 10 ml of water can be represented by the following equation. The value of delta H shown general dependence of enthalpy of solution on amount of solvent. As more and more solvent is used, the enthalpy of solution approaches a limiting value. The value is infinitely diluted solution for hydrochloric acid. This value of delta is given above the equation. Spontaneity. The first law of thermodynamics tells us about the relationship between heat absorbed and the work performed on by the system. It put only restrictions on the direction of heat flow. However, the flow of heat is unidirectional from higher temperature to lower temperature. In fact, all naturally occurring processes, whether chemical or physical, will tend to proceed spontaneously in one direction only. For example, a gas is expanding to fill the available volumes, burning carbon in dioxide, giving carbon dioxide. But heat will not flow from cooler body to warmer body on its own. The gas in container will not spontaneously contract into one corner, or carbon dioxide will not form the carbon and the dioxide spontaneously. These and many other spontaneously occurring changes are shown unidirectional changes. We may ask what is driving force of a spontaneously occurring changes. What determines the direction of a spontaneous changes? Let us first understand what do we mean by spontaneous reactions or changes. You may think by your common observation that spontaneous reaction in one which occurs immediately when contact in a mid between the reactants. If we examine the phenomena like flow of water down a hill or a falls of a stone on the ground, we find there is a net decreasing in potential energy of direction of changes. By analogy, we made to attempted to state that a chemical reaction is a spontaneous in given direction because decreasing in energy has taken place and as in case of exothermic reactions. Enthalpy diagram for exothermic reaction. It is a diagram for enthalpy of exothermic reaction. It is a diagram for the endothermic reaction, and it is a diffusion of the two gases in different forms. Entropy and spontaneity. Then we derive the spontaneous process in the given direction. Let us examine such a case in which delta H is equals to 0. There is no change in enthalpy, but still this process is spontaneous. Let us consider the diffusion of two gases into each other in a closed container which is isolated from the surrounding as shown in figure. The two gases, say gas A and gas B, are represented by a black dot and white dot, respectively, and separated by a movable piston. When a piston is withdrawn, the gas is being diffused into each other, and after a period of time, diffusion will be completed. Let us examine the process before partition. If we were to pick up the gaseous molecules from left container, we would be sure that these will be a molecule of a gas A, and similarly, if we were to pick up the gas molecules from right container, we would be sure that these will be a molecules of the gas B. But if we were to pick up molecules from container when partition is removed, we not sure that whether the molecules picked the gas A or a B. At, the, at this point, we introduce another thermodynamic function, entropy, noted by as the above mentioned disorder in the magnifications of entropy. Entropy is it is the measurement of randomness. Gives free energy and spontaneity. We have seen that for a system it is the total entropy changes delta S which decided the spontaneity of the process, but most of the chemical reactions fall into the category of either closed system or open system. Therefore, for most of the chemical reactions there are changes in both enthalpy and entropy. It is clear form of discussion in previous sections that either decreasing in entropy nor increasing in entropy alone can determine in the direction of spontaneous changes for the system. G is equals to H minus Ts. Gibbs function G is an extensive property and the state of a function. The changes in Gibbs free energy for the system delta Z can be written as usually the subscript system it is dropped and we supply write this equation. Sorry, we can simply write this equation delta G is equals to delta H minus T delta S. Thus gives free energy change equals to enthalpy change minus temperature into entropy change, and it refers to as the Gibbs equation, one of the most important equation in the chemistry. Here we have considered the both terms together for the spontaneity, energy in terms of delta H, entropy in terms of delta S. It is a measure of disorder. As indicated earlier, dimensionally we have analyzed, we find that delta Z has a unit of energy because both delta H and delta T delta S are the energy terms. Thank you.